Okay, let's continue talking about waves here. So imagine we have some string, or say, I don't know, a guitar string or some cable that's under tension. Then sound, waves can be emanated from that. Waves can travel through this string. So this thing is under tension. We call that tension force Ft. We have this guy mu here that is the linear density. That's the mass per unit length. So if I take some little delta x here, some little tiny length, times my mass per unit length, that would be the amount of mass in that little orange section there. So then the speed at which a wave would travel down this is given by this wave speed is the square root of the tension force divided by the mass per unit length. So if we increase the tension, if we tighten up a guitar string, the speed would increase. And remember, wave speed is lambda times f. Lambda is our wavelength. The length of a guitar string, if we have an open string, doesn't change. And that would be half a wavelength. If we tighten that up, we'd be increasing the wave speed. So then the frequency must increase also. V equals lambda f. If V goes up and lambda doesn't change, f has to go up. So tightening a guitar string makes the pitch increase. Pitch and frequency mean the same thing. What if we increase mu? What if we use a thicker guitar string, increase the mass per unit length, but we keep everything else the same? Well, then our wave speed would go down, which means our frequency would go down. That's why thicker guitar strings have a lower tone or a lower pitch. Okay, waves transfer energy. So I've got some wave, I've got some oscillator here that's bouncing this wave up and down. The individual particles, the molecules of the string, are bouncing up and down. They're not moving left and right. Energy is moving left and right at speed v. How much energy is being moved? We could go through the entire derivation. It comes from here. We're not going to go through the derivation. Here's the answer. This is how much energy is transferred in a wave. Depends on, so this is energy of wave on a string. Depends on the linear density, our angular speed, our wavelength, and our amplitude. Okay, what about power? Power is energy per unit time. Remember, power is measured in watts. So if we take our energy and divide by time, we'll get power. So our average power, our instantaneous power will be 0 because we're pushing and pulling, but our average power is given by this. Why do we care about power? Because we care about intensity. When we talk later in the next chapter about loudness, decibel scale, we care about how intense a sound is. And intensity is power divided by cross-sectional area, watts per square meter. So imagine we have some speaker in the middle of a room that's pumping out sound, that's pumping out energy in all directions. Imagine an expanding sphere around that speaker, and you're standing, I don't know, say 3 meters away from the speaker. That energy is expanding out in a sphere. By the time it reaches you, the amount of energy you're going to receive is the power divided by the surface area of the sphere you're standing at. Surface area of a sphere is 4 pi r squared. So the intensity that you'll feel or hear is the power divided by 4 pi r squared. Okay, and we'll talk a lot more about that when we get to decibel scales. Okay, sound waves. What if we have two sound waves in the same space? Sound waves follow the principle of superposition, which means sound waves add together like vectors add together. The amplitudes, the y values just add together. So I have these two waves traveling toward each other. They're just single peaks. They're not sine waves. I've just got this little bump traveling to the left or to the right, this bump traveling to the left. When they get together, they'll just add together. So when they meet right here in the middle, the total wave then will be twice as high. And then they'll just pass right through each other and keep going. Okay, so say we had in space this wave here. We're just taking a snapshot here. So this wave is oscillating in space and time, but we took a Polaroid of it and we froze it in time. And then we had this other wave that was also being generated at the same time. Well, what would the result be? We would literally just add all these y values together. So at this spot right here, I would have 1 plus 1. We would go up to 2. At that spot right there, 0 plus 0, these two waves completely overlap. 0 plus 0 would be 0, and so forth. We call this the principle of superposition. And this particular picture we're looking at here is total constructive interference. These two waves are adding together to get bigger. Okay, well, what if we had this wave, this blue wave, and this red wave at the same time, in the same physical space? Well, like at this spot right here, this guy says, I want to be at 1. This guy says, at the same spot and the same time, I want to be at -1. Those would add together to 0. Same with that spot there, 1 and -1, 0. That spot right there, a half and -1/2, 0. These two waves would completely cancel out. So if these were sound waves, this is what you would hear, nothing. This is how noise-canceling headphones work. There's some background noise. Noise-canceling headphones don't muffle the outside. They are speakers. They actually create new sound. So your headphones are listening to this sound. They create the same sound but 180 degrees out of phase. So that same sound but flipped over. So these two, this is what's coming in from the outside. Your headphones are creating an additional sound to cancel out that sound, and this is what you hear, nothing. Now, of course, when you have a lot of background noise, sometimes your noise-canceling headphones, they can't keep up because the background noise is noisy. It doesn't look nice and pretty like a sound wave. So it has a hard time figuring out what it needs to do to cancel that out. That's why you get some leakage and it doesn't completely cancel everything. But it tries, does the best it can. Okay, we call this destructive interference. This was perfect destructive interference because they completely canceled. And a lot of times we have some combination of the two. And altogether we just call that interference. Some places will combine together to get bigger, other places will combine together to cancel out and get smaller. Okay, so we might have, say, this wave here combined with this wave here. If we literally just add all the y values together, we would get a picture that looks like this. Now we can also do that backwards. This is called Fourier Analysis. This is the way we turn analog music into digital music. So we might have some sound wave that looks, really complicated like this. And Fourier Analysis decomposes that into a bunch of nice, simple, pretty sine and cosine waves. So you have some sound wave that's really complicated and looks like this. You run it through the analysis and it says, okay, I need so much of a wave that looks like this. I need a little bit of one that looks like that, and so forth. A whole bunch of nice, pretty sound waves. And then all you have to store is how much of each of those you needed. So you store just a list of numbers. I needed 7 of this, and 2 of this, and 5 of the next one, and so forth. You store those numbers in your computer, and you've recreated some complicated sound wave. Okay, standing waves, our last topic here in this lecture. So this is kind of interesting, but it's not a big deal here. If I've got, say, a string attached to a brick wall here, and I take it and I give it a little whip so that one little peak travels down and hits the wall. Well, that is going to stretch out my string here at the end, and that's going to bounce back, but it's going to come back inverted. If, on the other hand, I let this other end be free, like there's just a ring around a pole here, and I give it a little whip and I send this wave down, then this ring will go up and down, and that wave will come back reflected the same way I sent it down. So some musical instruments have a fixed boundary condition, waves bounce back inverted. Other have an open boundary condition. Horns, for example, have open boundary conditions, and the reflected waves will come back the same way they went down. Stringed instruments look like this. Horns look like this unless you put a muffle on the end, and you can make them look like this. We're not going to spend a lot of time on that at all. Yeah, there's a picture of that happening. Okay, so here is just another example of constructive and destructive interference. So I'm sending this red wave down. We have some other blue wave coming the other direction. These combine together to give us the black wave. So the black wave is the red and blue combined. Sometimes they overlap, like right here, they completely overlap. Sometimes they're completely out of phase, and the whole thing is flat. Okay, so imagine we've got this string here. It's nice and taut. We've got some force, some tension there. I've got this vibrator. It's going to take that string and bounce it up and down really fast. So that's going to be sending waves down that then will be reflected back. We're in this situation right here. But I'm not just sending one pulse. I'm sending a whole bunch of pulses down that get reflected back. And those will combine together like we're seeing here. So we can get pictures that look like this. We've got waves going down and back, down and back, down and back. And they combine together to give us, if we have the right frequency, something that looks almost static. Okay, so imagine you grab one end of a jump rope. The other end is tied to a wall. And you're bouncing this end up and down so that you get this nice pretty picture. The jump rope is just going up and down right in the middle. So yes, this end over here isn't really fixed. This is kind of an idealized, we pretend this end is fixed, but this end is really going up and down. Then your jump rope, you could imagine bouncing it so that the middle just goes up and down, up and down. We call this our fundamental frequency, or our fundamental standing wave. The frequency at which you're doing that would have to be perfect to make it do this. If you go a little faster, it would get all wobbly. If you go a little slower, it would get all wobbly. The wavelength that you have here is actually twice this length. So this is the length of the jump rope. Remember, a sine wave goes all the way up and all the way down. Like this dark curve here, right there, that would be one complete wave. So our wavelength here is twice L. L here is this distance, the length of the jump rope. So lambda here is twice L. This is our first standing wave, our fundamental frequency. That's the slowest you could bounce this jump rope up and down and keep it going in a pattern. If you were to bounce it twice as fast, so you double your frequency, then you would get a picture that looks like this. Now, of course, it's not going to look like this all the time, but what's going to happen is this middle spot right here is going to stay in the middle because you're sending waves down that are bouncing back and down and bouncing back and down and bouncing back. And those are constructively and destructively interfering with each other to give you a picture that looks like this, right? In the middle stays right in the middle. It doesn't bounce up and down. And this spot here goes up and down and up and down. And this spot here goes up and down and up and down. In order to get this picture, you would have to go twice as fast as you did here. This is our first harmonic. This is twice the frequency of the fundamental frequency. And we would have a node, we call these spots here, where everything cancels out in nodes. If you were to go twice as fast again, instead of having 2 crests, we would have 4 crests. And we would have nodes here, 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 here. So this pitch here, n equals 4, would be twice as high as this pitch, which is twice as high as here. So if you have an open guitar string, say your E string, and you pluck it, your guitar string is bouncing up and down just like this. If I go to the 12th fret on my guitar string and pluck it, it would have twice the frequency. It would be an octave higher, and my waves would look like this. If I go to the 24th fret on my guitar string and pluck it, I would get something that looks like this. It would be an octave higher again. So every time I double the number of crests, I go an octave higher. My pitch goes an octave higher. It's the same note, just twice as fast, an octave higher. These other nodes here, these other standing waves, we call harmonics. Well, they're all called harmonics, but these harmonics would not be the same pitch. So when you listen to a particular note on an instrument, you're not just hearing a pure note. If I play an E note on a violin, you're not just hearing a pure E note. The wood is vibrating, the string is vibrating, the air around, the air inside the violin vibrates at a bunch of different frequencies. We're mostly hearing the E note, but then we're also hearing some of these other notes. These go on forever, and we call those the harmonics, and that's what gives a particular instrument its timbre. That's what gives it its tone. It's the combination of all the different harmonics or overtones we're hearing. And that's why a violin sounds different from a piano, sounds different from an oboe, sounds different from a horn. All the different instruments sound different. It's why one violin sounds different from a different one, because we have different combinations of overtones, even though they're all playing the same fundamental note. So all these different overtones or harmonics are all multiples of this fundamental frequency. So F1 here was that fundamental. His wavelength was twice L, plugging in n equals 1 here. And all the other harmonics are multiples of this guy. We would just plug in n here. If I wanted the fourth harmonic, I would plug in n equals 4. And again, we call those overtones.